A coin with heat capacity 15.0 joules per degree Celsius at 48.0 degrees Celsius is thrown into a glass of 25.0 grams of water at 12.0 degrees Celsius. If the glass does not absorb or release any heat, what is the final temperature of the mixture? Specific heat capacity of water, Cp, equal to 4.184 joules per gram per degree Celsius. Alright, so we're looking at a heat problem. And this problem contains apparently more than one object. And whenever we're dealing with multiple subject in a heat problem, chances are there are interaction between them. There are heat gains, there are heat losses. And the only way that we know how to solve this type of problem is to look at the entire system involving the multiple objects as an insulated system. Otherwise, we wouldn't be able to calculate it. Alright, so if this is an insulated system, then we always have Q lost plus Q gain equal to 0. Alright, so this is going to be our starting point. So who's losing and who's gaining? The coin has original temperature of 48 degrees, so it's hot. Glass of water is having 12.0 degrees Celsius, so it's the colder object. Now, and the glass didn't do anything, so we can exclude it from our system. And now that makes things pretty simple. We have a coin that lost heat, and we had some water that gained heat. And whatever amount heat the coin lost must be all absorbed by water. And the total of it, one positive absorbing, one negative losing, equal to 0. Alright, so how do we calculate these two heats? Depends on what kind of condition we have. For the coin, we have heat capacity, joules per degree Celsius. This has nothing to do with mass, nothing to do with moles. So, of course, this Q can be calculated with a simple heat capacity times temperature change, C delta T. And for water, we do know mass, and we're getting a specific heat, Cp. So you know what you're going to use. Got to be mCp delta T. These two add up equal to 0. Now, let's see how do we calculate each of them individually. The coin, heat capacity, C, 15.0 joules per degree Celsius. Delta T, oh, we don't know the final temperature, but the final temperature, we're looking for the final temperature of the mixture, which means by the end of it, these two, to stop that heat exchange, these two got to be at the same temperature. And let's call that temperature, final temperature, TF. And we know delta T is final temperature minus initial temperature. We don't know the value, but we can use TF minus initial temperature is 48.0 degrees Celsius. And of course, degrees Celsius will cancel. Plus mass of water, 25.0 grams, times Cp, 4.184 joules per gram degree Celsius. Gram cancel. And delta T again. Now we don't know the final temperature, but it should be the same TF. minus the initial temperature of water is 12.0 degrees Celsius, and degrees Celsius cancel. And the total of this calculation should equal to 0. So let's write it out. 15.0, now both are joules, so I'm going to omit that unit right here, times TF minus 48.0 plus 25.0 times 4.184 times TF minus 12 equal to 0. This is a simple mixture calculation. Put all your TF together on one end. If we open up the parentheses, we got 119.6 TF on the left side, and move all your number to the other side. Now, the two numbers moved to the other side, it would give you 1975.2. And of course, you can calculate TF very easily at this point, and that's going to be 16.5 degrees Celsius. So once you throw this 48 degrees Celsius coin into the cup of water at 12 degrees Celsius, coin would lose heat, and temperature goes down all the way down to 16.5. And for water, after absorbing the heat released by the coin, the temperature would increase and would go all the way up to 16.5 as well. And 16.5 is our final temperature of the mixture. So whether we have 2 objects or 3 objects or even more in our insulated system, as you can see here, it doesn't matter. Some of them are going to be losing heat, some of them are going to be gaining heat, and overall, as long as they stay in this system, the total of heat gain and heat loss eventually equal to 0. And all you need to do is figure out who's losing heat, who's gaining heat, and using the condition that you were provided with to break it down and into different heat calculations, and rearrange the equation and do your calculation.